In probability theory, we work with many random variables x, y, z, etc. that are jointly distributed, and often we also want to work with their functions like this, or we may even like to combine these random variables together in a multivariate function like this. Now, if we are given the distributions of these random variables, we are generally interested in finding the distribution of their functions. Starting with this video, we are going to explore some such techniques. The simplest such technique is using CDF. The CDF technique works particularly well when we are working with a single random variable and some function hx, where this h is monotone. So the idea is you start with the distribution of x, and from that you work out the CDF of y equals hx, and then possibly differentiate it in order to arrive at its density. Let me explain the technique using an example. Here x is uniformly distributed over the interval 0 to 2. Your job is to find density of x squared. Observe that x squared is a monotone function because we are only working with non-negative quantities. First we give a name to the transformed random variable, we call it y, and let gy be the CDF of y. Every random variable has a CDF. So gy means probability y less than or equal to little y. Now observe that x lies between 0 to 2 and y is its square. So y has to lie between 0 and 4. So you can immediately see that it will be equal to 0 if y is less than 0, and will be equal to 1 if y is greater than or equal to 4. So the question is, what happens in between? To answer this question, we take some y in this range. Then we want to express this in terms of x. Because y is x squared, I am just replacing y by x squared. Now, fortunately, x squared is a monotone function because we are working over non-negative things. So I can take the square here and make it square root without sacrificing the inequality. So I have this. Now, y lies between 0 to 4. So square root of y, the positive square root of y, lies between 0 to 2. So I know that it is uniformly distributed from 0 to 2. And I am interested in the probability that it lies to the left of root y. What I'll do is, I will take length of this, divide it by the total length, and that will give me root y by 2. So I have worked out what I should write here. It should be root y by 2. So I have obtained the CDF of y. They asked me to find the density. So now what I will do is, I will just differentiate it to get 1 by 4 root y if y lies between 0 and 4. I am doing the non-trivial thing first. And here it is constant, so derivative is 0, derivative is 0. At the end point, it is not really differentiable, so there also I set it equal to 0. So I get 0 else. In fact, I cannot immediately say that this is density. What I should now really check is, if I integrate this from minus infinity to y, whether I get this back or not. Well, in this case, there will not be any problem. So generally what people do is that they are just lazy and they just leave out that check. But strictly speaking, you should now check and show that this will indeed give rise to this CDF, and hence conclude that this is the required density of x squared. The last example was very typical where we worked with a monotone transform. Now sometimes the CDF method can also handle non-monotonic transforms like this. Very similar to the last problem, except that now I am working with -1 to 1, but still my transforming function is x square, which is not monotone over this interval. Again we proceed just as before. Now I ask myself the question, what are the possible values of y? You can see that the possible values of y are now from 0 to 1. Hence, I can automatically write down 2 lines. The only case that I have to worry about is the in-between case. And as usual, I shall start by taking one such y and express this probability in terms of x. Now comes the difficulty. Earlier I could take t square on the other side without disrupting the inequality. Now I cannot do it. But that is not a big problem, because if x square is less than or equal to y for some such y, we can easily work out the values of x. So here is the graph of y equal to x squared. I have taken some y in between, so all that I need to do is to drop these 2 lines. Then this is minus root x root y, and this is root y. So x has to lie between these 2. Now we have to find out the probability. So x lies in an interval. I am told that x lies in -1 to 1 uniformly, so I am interested in the probability that it lies here. I can find that by taking length of this and dividing by the total length, which means it is this, and of course the 2 2's cancel each other out, and I know what I should write here. And as before, I will now just differentiate this whenever I can and set it equal to 0 whenever I cannot, to get this function, which I should ideally check that if I integrate it from -infinity to y, I will really get my capital Gy. In this exercise, I give you a random variable x that has constant density. I am not telling you what constant it is, over the unit interval, and 0 outside that interval. Now your job is to guess the density of 1 minus x. So first just think intuitively. You should be immediately be able to answer this question, and then you can check your guess using the CDF method.